Optical Sensors, presented by Jocelyn Chavez, Len Mack, and David Rodriguez. This video will cover how they work, their applications, and the economics. An optical sensor is a device designed to measure the electromagnetic waves in a wavelength spectrum ranging from UV light to infrared. The basic configuration of optical sensors relies on photodiodes. A photodiode refers to a p-n-type semiconductor system used for its ideal photon-electron relationship. These semiconductors are termed p-n-type because of their p-n junction. This junction serves as a barrier to electron flow. In order for the electrons to overcome the barrier, a second energy source must be available. Light waves received in the form of photons excites the electrons through the barrier and produces a measurable electrical current. The intensity of the light, or photons, determines the magnitude of the current. p-n junctions are created by placing a p-type semiconductor adjacent to an n-type semiconductor. For the purpose of this video, silicon semiconductors are considered. A silicon atom has 4 valence electrons. A pure silicon structure forms fully filled, very stable covalent bonds. Doping pure silicon semiconductors with electron-rich gas, such as phosphorus, produces an n-type semiconductor. Phosphorus acts as a substitutional impurity, resulting in free electrons. Similarly, silicon doped with boron produces a p-type semiconductor. Boron is 1 electron short, resulting in a hole within the structure. Optical sensors play a role in all facets of life. They can be found in your computer, your cell phone, as well as your car. A multidisciplinary example, presented next, will demonstrate how these sensors can help on a microscopic level. A biomedical method of application introduces flow cytometry. A flow cytometer is an instrument capable of characterizing specific particle parameters such as membrane complexity, cell size, and fluorescence. A flow cytometer accomplishes this by emitting a known wavelength through a cell or particle. Optical sensors located at different locations then capture the emission of scattered wavelengths and measures their intensity. This information is carried via optical fibers. The scattered light traveling through these strands reaches a secondary device that converts the signal into a readable language such as voltage. As we can see, optical sensors are an integral part to larger systems across a variety of industries. As a result, collaboration between a range of different kinds of engineers is needed. Luckily, the production of these devices is inexpensive and does not greatly contribute to the pollution problem we face today. Many of the components, such as semiconductor material, are naturally occurring minerals. Optical sensors are very common in a variety of fields. The largest shareholders are industries specialized in consumer electronics. Other industries include automation, energy and utility, military and defense, and many more. Although optical sensors are already efficient and precise devices, new markets and applications are constantly arising. Improvement and innovation in this field will always be necessary.